Hello everyone, today we're going to be talking about the normal distribution. Now you might recognize this shape, or it's sometimes called the bell curve, right? So we talk about a bell curve. You know this comes up a lot kind of naturally in nature, right? That there's kind of like a middle that's a peak and that kind of tapers down on the end. Like you might hear that maybe the performance on a certain test was a bell curve, there was a peak in the middle, kind of turns down. Now this one with this graph starts at 0 with the peak and kind of tapers down the other directions. So the general formula for the normal distribution, again, the normal distribution, it could have the peak at any point, could have any mean, any standard deviation, is this formula. Kind of complicated, right? But let's break down what this is saying. This little mu symbol is the mean, and this little symbol is the standard deviation. That's pi. But if you're concerned, like that equation looks kind of scary, right? Now, that equation would produce this graph that goes up and down like that. However, you don't really need to know how to use this equation in particular because there are some really cool properties of the normal distribution. In particular, there's something called the 68, 95, 99.7 rule. This says that 68% of your data, so you see right here in the blue, is within one standard deviation. So if you got your mean in the middle, and you got the mean minus standard deviation, mean plus standard deviation. So to break it down, let's think of an example, right? Let's say I said the data had a mean of 50, and let's say mean is 50, and let's say the standard deviation, you could use this symbol or you could use an S. But the standard deviation, let's say, is 10. Make it easy. So if this number is 40 and this number is 60 then, because that's 50 minus the 10 and 50 plus the 10, that means that 68% of your data is going to be in between 40 and 60. Likewise, if we go down one more standard deviation, I use the number 10 because it's easy. If you go between 30 and 70, that's kind of highlighted by this green area, you see that 95% of the data would be in between those two numbers. Go one more standard deviation, and you've got 99.7%. And again, standard deviation itself is kind of a weird formula. They're like, why do you use standard deviation? Well, because it comes up a lot in formulas and theorems like this, with particularly the normal distribution. It fits very nicely if you count by a certain number of standard deviations. Again, this would be like, let's say between 80 and 20, 99.7% of your data is going to be in between 20 and 80 in that case. So let's see how you would apply that knowledge on an example problem. See, this example problem uses the same numbers I gave earlier. Let's say there's a set of data that's normally distributed with a mean of 50 and a standard deviation of 10. What is the probability that a randomly selected tree is in between 40 and 60? Well, we just showed that on the graph earlier, but let's say this was a worksheet. You didn't have your graph. You could kind of think, okay, wait, if I got 50 in the middle, if I got 40 and 60, wait, that's one standard deviation. One standard deviation, 68%. Ding, 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 easy, right? And then you're like, okay, between 30 and 70, you might not even need to draw your table. You could double check, though. You could say, okay, 50 minus 10 is 30, and 50 plus 10 is 70. So it confirms easy, right? 95% is the answer here. 95. A little more space for this last one, so we just see it's going to be the same process. You got 50 minus, we could just say 3 times 10 would give us 20, and then 50 plus 3 times 10 gives you 80. So clearly that is exactly what it's asking, is 3 standard deviations, so that is 99.7 based on our rule that 3 standard deviations is 99.7. Alright, let's look at another example. The heights of trees in a certain forest are normally distributed with a mean of 47 feet and a standard deviation of 13 feet. Now, this is a great real-world example because this is where the normal distribution shows up a lot in nature. When you measure the heights of a certain plant or animal, or if you measure the weights or a certain attribute of those, a lot of times they follow a normal distribution. So, what's the probability that a randomly selected tree is in between 30 feet and 60 feet? Might seem hard, but let's just check. I wonder if you did 47 minus 13, what you'd get. Turns out you get 34. Ooh, if I do 47 plus 13, I get 60. So that means that this range is the range of one standard deviation. So we know by the rule that's 68%. Yay, easy, right? Now let's try this one. 47, if we want to subtract 13 twice, we could do it like this. Minus 2 times 13, and that would give us 21. 47 plus 2 times 13. You could plug this in a calculator just like that if you want to double check. Gives you 73. So this is 2 standard deviations, 95%, all right? And then if I check this one, you're probably guessing, yes, it is in fact 3 standard deviations. If you subtract minus 3 times 13, you'll get 8. And if you do 47 plus 3 times 13, double check me if you want to, but of course you will get 86. This means 3 standard deviations gives you 99.7%. Wonderful. So you've probably seen clearly these problems are specifically designed so that it is a specific number of standard deviations, right? However, most problems, like especially that come from the real world, you don't necessarily want to know exactly between standard deviations. Or in a problem like this, what if I want to know between, I don't know, 30 feet and 80 feet, right? If you want some numbers that don't exactly fit on certain numbers of standard deviations, how do you calculate it? Well, that's what we're going to look at next. Here's another real-world example. Let's say the weight of newborn babies born to full term to a mother 20 years of age or older follows a normal distribution with a mean of 3,510 grams and a standard deviation of 385 grams. So if you randomly select a baby from this group, what's the probability that it's between 3,000 and 4,000? So right away you can tell it's probably not an exact number of standard deviations. You could try it and say, let's see, if I did 3,510 minus 385, that would give 3,125. And then, let's say I subtract one more standard deviation. If I minus 385 again, plug that in, that would give you 2,740. Okay. So I passed over the 3,000. It's not exactly going to work. So the kind of traditional way to do this, the way that my dad learned in school, that they still kind of teach in this school, is to use something called a z-table. Looks kind of like this. And first you basically got to use this formula. You got to calculate a value for z by doing each value minus the mean over the standard deviation. And then you look it up in this table. Like, for example, if you get a z value of negative 2.64, you'd go to negative 2.6, go to 0.04, and this would be your number. I think, why are we doing this in 2025, right? Because this is not even the fundamental math. The fundamental math, if you really want to do it, is an integral, right? If you want to do calculus, this is how you actually would calculate the probability. You would integrate between the two values. But we don't want to do calculus. And why are we just looking up numbers in a table when it's 2025? Let's use a great online tool. So there's a website called StatTrek.com/onlinecalculator-normal, and there's a lot of online normal distribution calculators, and in reality, there's no professional out there that's using z-tables. They're going to have some computer system that's going to calculate things. We got to know how to use them. Now, so first of all, if we think about our other example problem, we don't have the z-scores, we just have the raw scores. So if you're talking about the actual numbers, like I want the baby weight between 3,000 and 4,000, I'm going to click raw score. And now, do I want just a probability of less than x? No, I want actually a range. So we're going to pick this one, x1 to x2. So our population mean for this problem was 3,510, and then the standard deviation is 385. So that's what we're going to input here. So I type these numbers in here, and then our minimum value, remember the problem asked between 3,000 and 4,000. So I'm going to type in 3,000, 4,000. Now the cool thing about this is if you just leave one blank, it'll tell you the rest. So for example, if we wanted, hey, what range starting with a minimum of 3,000 would have 50% of the data, we could put 0.5 in here and then leave that blank. But what we're doing is we want this. So what I'm going to do is I leave that as the one blank. I hit calculate. Boom, I got it. 0.8058. So as a percentage, that would be 80.58. So my answer here would be 80.58%. Sweet. Boom. See how using these online tools makes it super easy? We just have to understand how to use it. So let's look at this last problem. What's the probability that one of these babies will weigh less than 2,000 grams? So now when I go over to my calculator, instead of a range, I want less than. So I'm going to click here, click just less than x, and now my x becomes 2,000, and I calculate. Easy, right? Boom. So what I get, 4e negative 0.5, what does that mean? Well, what that means, the nice thing about this is not only does it give you these numbers, I didn't show you, it also shows you like this graph here. So notice that 2,355 is like there. Less than 2,000 is pretty small. Now, To really elaborate, what does that mean? You probably know in the calculator. That is shorthand for scientific notation. So that means 4 times 10 to the negative 5. So we could write that here as our answer. 4 times 10 to the negative 5, or in terms of probabilities, it's approximately 0, right? So if this is the real normal distribution, the probability that the baby is going to weigh less than 2,000 grams is extremely unlikely. Now, again, of course, in real life, sometimes it will deviate from that. There's going to be one person out of millions that has a baby that weighs that small. But in general, if it's perfectly following the normal distribution, your probability of less than 2,000 is going to be very small. Let's just do one more example to close this out. So a candy factory attempts to make chocolates that are exactly 1.5 ounces. In reality, the chocolate produced follows a normal distribution with a mean of 1.5 and a standard deviation of 0.03 ounces. Now guys, this is a really cool actual real world application. Most factories, or most times you mass produce things, the way normal distributions most often show up is if you look at the attributes of animals that are born or that live, like the height of adult males follows a normal distribution. The weight of babies that are born. If you look at any quantifiable characteristic, usually it follows a normal distribution. And also, even human-made factories, they're not perfect. You're not going to make every chocolate exactly 1.5 ounces. Even if it's really close, there's going to be some variance. Notice that standard deviation is 0.03. So, what is the probability that if you buy a chocolate bar, it weighs between 1.45 and 1.55? So, let's highlight the key numbers. We've got 1.5, this is the mean, 0.03 is the standard deviation, and we want in between 1.55 and 1.45. So what I'm going to do is I'm going to go back over here, I'm going to change this to a range, I'm going to say my population mean was 1.5, the standard deviation was 0.03, and I wanted in between 1.45 and 1.55. So if I calculate 0.90442, pretty good, to about 90%. We could probably say 90%. It doesn't say on this problem how much to round it, so I'll put the pretty much exact thing. So about 90%, 90.442%. Cool. So 90% of the bars are going to be in between that range. Now in real life, the factories may be a little more precise. I don't know if there's that much variance. I kind of made this one up. Now, what's the probability that a chocolate bar weighs more than 1.6 ounces? So again, we go over here. And we could do the greater than this time. We type in 1.6, calculate, and we've got 0.4779. So 0.4779, sorry, 0.04779 would be about 4.779%. So it's not as astronomically tiny as the last problem. So you're having, about 4% of the chocolates that are more than 1.6. Again, a real factor would probably be a little bit more precise, but it kind of shows the overall principle that it is true, that even things mass-produced in a factory usually have a variance or standard deviation with a mean that is that goal amount. So hopefully this helps with how to calculate. Now using that tool, StatTrek, you can calculate any probability from something that is a normal distribution.